So the last time we looked, we saw that we were drawing incredibly quickly. Our buffer updates were fairly good, and the slowest part of our simulation path now is this update part of it, which is taking quite a long time. And we're going to look at how we can speed this up. So this next demo, we're going to try and utilize all of the cores within the machine. So this is a hex core machine, so in theory I should be able to utilize all 12 cores when I'm running the program. Now I'm just going to show this in action, and I'll show this one in action at the same time. So what we can look at here is this is the demo that's now multi-threaded, and this is the demo that's single-threaded. And the first thing you'll notice is I've actually made my performance worse. And I've made my performance worse by quite a large factor, which is a bit worrying because, you know, surely this should be getting better. Well, there are some caveats with this, and it's to do with load and what work's going on. So if we look at our task manager, and actually more particularly what we want to do is look at our resource monitors and what's going on here. If we look at the textual fetch demo, we can see, and the threaded update demo here, we can see that this is now using more threads. So it's got, keep disappearing, there we go. So you can see how much CPU load that's going on. In fact, my threading doesn't appear to be doing particularly much there, any difference, but when I run this on the Mac, you can monitor the individual threads quite easily, and you can see that the threaded update is doing a lot. Let's just go back and close these simulations and give it more work to do, because this is actually where threading really comes into place. So let's do 1, 2, 3, 4, 5, 6. So actually let's just do a lot of particles minus n1, 6. So what we're going to do now is fire up our simulations with 1,000,000 particles. So again, you can see here my draw relatively quick, my buffer update not too bad, but my update here now, you can see it's taking 340,000 microseconds for that 1,000,000 particles, which is, you know, very slow. Whereas now you can see that this is taking about 78,000. So we have now got a significant speed up in what's going on. Texture buffer updates are roughly the same, drawing roughly the same. It's hard to tell the difference, but you can see the sluggish nature of me rotating and zooming now with this. It's taking a lot longer, it's a lot slower to do so, whereas this version is a lot more responsive, using a lot more, and also now you can see I'm getting good utilization out of all of my cores from this program, whereas before my cores really weren't you know, doing too much. So this app, you know, it's got this 10 threads, CPU load at 40 something, threaded update here. You can now see, look, the average CPU load that's coming through here is much higher than this version. So I'm actually exercising my CPU, I'm exercising my cores, I'm doing a lot more work, and you can see here now that the thread counts are going up and down as and when I use and join my threads, and it's a lot more efficient. Now, there are a number of ways of doing this and making things go multi-threaded. One of the ways of doing this is to use OpenMP. And it has a very nice parallel for loop, which when we've got something that's embarrassingly parallel, makes our life very easy to set up. Unfortunately, that doesn't work on the Mac. So what I've done is I've decided for this demo is to use C++11 threads to start with, just to sort of demonstrate the processes and give people the understanding of how these threads work. So I'm hash including thread, which is the C++11 native threading code. And down here you can see I'm creating a very simple std vector of threads, which I'm calling mthreadpool. The rest of the code is exactly the same as before, still using the TBOs to update and everything else like that. Now, when my program starts, what I'm going to do is I'm going to query how many threads there are in my system. So n number of threads is making a call to std thread hardware concurrency. This will return how many threads we've got available to our system, and then I'm resizing my thread pool, and you can see, when I do run this, you'll see when I'm running this, creating 12 threads in the pool. So this is saying there's 12 threads we've got available. So I recreate my thread pool to be 12 threads, and then my update system now is going to do the following. So I'm looping from 0 to the number of threads, and then what I'm doing is I'm creating a std thread based on this lambda function here, and this lambda function is basically going to partition my work into chunks. So what I'm doing here is basically my chunks are based on the number of particles divided by the number of threads, and I basically loop through each time and partition into chunks each one of these threads, and I will then effectively, I'm partitioning. So maybe depending on how many threads we've got, I've got 12 there, I will divide through 12 by the million that I've got, and then I would get a chunk of threads from 0 to 120,000, then from 121,000 through, and so on. I can't do the maths in my head straight away, but the work is being partitioned in that way. So now all of a sudden my work is running across multiple threads by, as you can see here, joining those threads. So it's a very, very simple sort of process, but with this embarrassingly parallel algorithm where other elements don't need to worry about each other, so we don't need to worry about mutex and locking values or anything like that, we can just say, right, fire that work off and get it done quickly in parallel. And that's what this is doing. Everything else in this demo is exactly the same as before. It's just the fact that update now basically partitions the work based on the number of threads and different chunks, and then goes off and evaluates it. Now, it's most probably worth, when we're writing code like this, putting a check in to make sure it's worth doing threading. And it takes a little bit of balancing to determine the best way of doing this. But what you can do is say, if the number of particles that we need to simulate is less than some threshold, run it single threaded, because the overhead of creating the thread and joining the thread is what slows things down. And that's what you've seen when I just run, if I run 100 in a threaded update, it's, in this case, it's still generating 100 threads. If I run 100 there with this demo, now you can really see that the overhead of creating threads is not worth the work, because in this version where I've created a thread, I'm still taking this big time for 100 particles, whereas this is taking no time at all. So it really is a matter of, deciding what the threshold is. 10,000 is still fairly slow there. It's most probably going to be of the order of 100,000, where the overhead of threading is going to make it faster. So I'm on at the moment about 2,800, and there I'm on 80. So no, not even that. Oh, actually, that's got more. That's 100,000. Yeah, that's up. Another few in there. There we go. That's about the same. So 100,000 threads is definitely better. So you can see that that's taking a lot less time and so on. So again, it's a matter of analysing your problem and determining how your problem frame works with that. But that threaded update works, really nice. It's a very easy win for simple things like that. As I say, you can also look at using OpenMP, but OpenMP isn't supported on the Mac. In the next video, we're actually going to look at a better alternative, which is, again, exactly the same process, just a lot easier, using threaded building blocks.